So now we have to ask the question, what is it are we solving? What are we trying to solve? Well, if you think about it, and this kind of does take a little bit of a step back. So if you're new to networking, maybe you'll have to go read some history books or talk to some older folks. If you've been around for a while, then you probably remember back to before we even had VLANs. We still had hubs or bridge domains, and we separated those through routers, right? We broke up broadcast or bridge domains through routers. But then, these new fancy Cisco, or actually Crescendo switches that Cisco acquired for the Catalyst line of switching, introduced, I think it was '98, this concept of VLANs. Now, a VLAN, or virtual LAN, of course, was a way to have multiple separations or multiple LAN, multiple broadcast domains or bridge domains on a single physical switch and break up those broadcast domains. We have to ask ourselves, why did we need to break up the broadcast domains? Well, because there was a lot of broadcast. Of course there was. What kind of broadcast? Well, the number one kind of culprit of broadcasts is ARP, of course, right? Address Resolution Protocol. We have to resolve a MAC address for an IP address so that we know at a layer 2 Ethernet level where to forward traffic on the network, on the switch domain, which of course is done through MAC addresses. So VLANs were used, but they were kind of tightly coupled with subnets. So could we have multiple subnets with one VLAN? Well, you could, but it typically was kind of shunned, right? So if you ever walked into a network and you saw 15 separate IP addresses, so IP address and then IP address secondary, IP address secondary, 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 on a single SVI, which I'll say a lot, so switch virtual interface, or essentially interface VLAN, okay? Or even on a routed interface. This was typically shunned, typically a bad idea. Why? Well, because we had a lot of separate broadcast domains on one particular bridge domain, or VLAN, if it happened to be that. And again, this was because we had a lot of broadcasts. We had ARP. We also had unknown unicast flooding. And there's some other things as well, certainly, but those are the two predominant ones. So we'll talk about how ACI basically eschews the need for those, or obviates the need to have those ARP, or eliminates the need to have ARP, or unknown unicast. Now, of course, there's times when we want to or have to turn it on, and we'll certainly discuss all of those throughout the course and series of these modules as well. However, we do have the ability to turn it off, and actually it's off by default for every bridge domain. And again, we're going to talk a lot about bridge domains. We're not going to use the word VLAN a lot because in ACI we're not using VLANs, we're using VXLAN. Now, of course, VLANs are still very important to us. We still have to learn VLAN information through .1Q trunks, through our southbound devices into our leaf switches. But once, and we'll demonstrate that on the whiteboard a lot more. But once we've learned that VLAN ID, we strip it and we map it to a VXLAN. And so we'll just simply refer to these as bridge domains. So we'll talk a lot more about that. But we've typically had, getting back to the slide, one subnet per VLAN was the general rule of thumb. And we then placed constructs on top of that. So our network policies for permit, deny, QoS mark, or possibly redirect through policy-based routing or logging with ACLs, permit deny as well, ACLs. We based those on subnets, which were based on VLANs. Our SLAs, our QoS, was based on VLANs. And even L4 through 7 services, okay? We based those on VLANs, or we routed traffic, or really kind of herded traffic via our VLANs. So network constructs got overloaded with unintended, or at least originally unintended, functionality. The other main issue is we have a huge language barrier. So why does our data center exist? Now you may say, why do I care about developers? If you're a developer watching, then obviously you know the answer to that. But if you're a network guy, you might say, why, or girl, why do I care about developers? Well, without them, there's no need for a data center, right? Applications are the reason that we have our data center. So there's been a huge disparity between developer language and infrastructure teams. So developers talk about things like application tiers, provider-consumer relationships, and API call flow. Infrastructure teams say, I don't know what you just said, but I need to know how many VLANs you need, how many subnets you need, what protocols and ports you're going to need to have allowed, and if you need load balancing, or do you need, next gen, or firewalling or deep packet inspection, or anything like that. So we have to have someone to translate between these disparate languages. So another issue, and this is really a huge issue, so we'll take a little bit of time to talk about this. Here's just a very simple 3-tier application. We've got our, and when we say 3-tier, we've got our web server tier, our application server tier. So let's say this is an Apache web server, a Tomcat application server, and a MySQL database. Very common stack for application development. And of course, we have our outside users. Data centers they run a lot better without users, but obviously limited need for them without the users. So we need the users coming in from the outside. To get in from the outside, we want to obviously route that traffic in, so they come in through a layer 3 firewall. Now we probably have multiple firewalls, so they probably come in through a switch, and we have a VLAN defined through that. So we have our initial switch with a VLAN and our router config. And this is only showing one switch and one router, and we now have either 3 separate switches with VLANs, or we could even use the same physical switch with separate VLANs, but security policies typically dictate multiple switches. And of course, we're going to have redundancy in switches. So if we see 3 switches here in one router, we haven't even got to the firewall yet, really double that because we want redundancy. So then comes in the firewall configuration. Next comes another switch with our next VLAN, as well as our SSL offload and load balancers. Okay, so here's our load balancer. And my animation is slightly off. So we're now extending from the VLAN, from the switch, down into the web tier. And now we also have possibly another firewall, so that those web servers can then get down through the load balancers into the application tier, where we have at least one more switch with a few VLANs, or a few more switches possibly, probably one switch. And then either a firewall or maybe just regular, no firewall, but just a switch config with maybe an ACL before we get down to the database layer. And again, all of this is just with single devices. We haven't even gone into the duplicate devices that we would have for redundancy. Now, maybe they're VPC and we're using config sync. Just kidding, don't use config sync. But you get my idea. Double all this work. Now, think about this. That's not only a lot of work to do, but this is we're doing these on most likely production switches that have, shockingly, other traffic on them. So they either have to be done at a maintenance window, if we want to be safe, or they have to be done in a way that isn't going to affect anything else. So if we have a human doing this, raise of hands, real quick, don't worry, I can't see you. This isn't a live class. Who has ever configured a distribution/aggregation switch, and you've gone to run switch port mode? I know these are all switch port mode access, but let's say switch port mode trunk, of course, was already configured, and switch port trunk allowed VLAN was there, and you had a list of VLANs. Well, now we need to add a new VLAN for this new application. And this is the reason why we have what in DevOps terms we would call a waterfall deployment, meaning we save up all the changes that we have until a maintenance window, and then we make it during a maintenance window. So everything just waterfalls all at once. All the changes get pushed immediately during a maintenance window. And then we, of course, have regression testing to make sure that everything still works. Why do we do those maintenance windows? Well, again, show of hands, who has ever gone to add a VLAN to a production aggregation or distribution switch and issued the command switch port allowed VLAN or switch port VLAN allowed? I can never remember which comes first. Question mark, right? Switch port VLAN allowed, the number of the VLAN, enter. and you think, I forgot to hit add. It's too late. It doesn't matter whether we were in a live environment or not. It doesn't matter if you can even, well, first of all, you'd have to go back and remember what all VLANs were allowed, because probably PCI or other compliance is going to require that you not allow all VLANs. You can't just have switchport mode trunk. Also, it could really impact the traffic flow. So now you have to go back in your change history if you keep regular backups of your configuration files, which hopefully you do. And you have to remember what all VLANs were there that I need to add back. This is a problem. Actually, if you've ever done that, and that was the show of hands, right? Behind the screen, I can't see you. If you were honest, either you've never done it and you just started in networking, or you've at least done it once. I doubt there's many people out there that have never done that, not even once, in a production network. Which, that can be a RGE, a resume generating event, depending on how important the production traffic was or the production switch that you hit. It might be a CLM, a career limiting move, because that word might get out to other people and other companies. The idea is that humans make errors, and waterfall deployments, or everything all at once, even during a change window, is potentially catastrophic if you don't have proper regression testing. And if you're doing it during a live production deployment, even more so, possibly catastrophic. So this is some of the major problems. So that's not even talking about the redundancy, or what if we add a few more web servers? Well, now we need to go back to the switches, back to the load balancers, and make some changes. So let's talk now about what is an application as it pertains to the network. Well, it's more than just a virtual machine or a bare metal server. It's really a collection of all the application's endpoints, plus the layer 2 to layer 7, really layer L4 through 7 network policies, including L2 and 4, right? We might have VLAN ACLs, we might have layer 3 ACLs. So the idea of what we want to get to is to build teamwork, to create a logical, abstracted, stateless model that supports the application. So we create our model, we define the endpoint groups, which of course are simply collections of endpoints. And by the way, we'll refer to these endpoint groups as EPGs. So this is a term you'll hear quite a lot in all the future modules for ACI. We define any layer 4 through layer 7 services like firewalls, load balancers, IDS, IPS, network data broker, or monitoring, Gigamon, things like that. We create this logical model that supports the application. We create our contracts. Well, we'll actually talk a lot more about that. We haven't defined that yet. Our contracts are what allow, okay, in the same way that, think of a contract. If you go and get a job, you interview, maybe it's a higher level position that requires a contract, maybe it's just a regular job. You essentially have a contract, whether it's legally binding or not, that basically says, you know, you will provide work and your employer will consume the work, right? Your employer, on the other hand, they will provide you with a paycheck, and you will consume that paycheck. You'll put it in the bank, you'll be a consumer, you'll use that money. So you essentially have this contract between two different parties. Well, think of our different endpoint groups as the parties. The web server is, let's say, for instance, let's just say the outside EPG is the user or person going to work. And the web server is the boss, right, the company. So the web server provides a position and you consume that position, right? So they provide the paycheck, you consume the paycheck, and then the outside EPG, it does the work, okay? And we'll talk about single contracts with bidirectional filters much later, and we'll also talk about unidirectional contracts, but multiple. So another relationship where the outside EPG provides work and the web server or boss or company consumes the work. Okay, so we'll talk about these provide-consume relationships for contracts. And the contracts define what happens. So who's the provider, who's the consumer, what are the ACL or stateless or stateful firewall rules that are being implemented in the ACI fabric, so in the ACI leaf switches, or if the contract is told to use, let's say, an outside or external firewall, load balancer, SSL offload, IDS, IPS, things like that. So these are our service policies. We'll define all these logical constructs in the APIC, and then from there, we will deploy these. So these will be packaged up into an application network profile, which then get instantiated or pushed out to the fabric, to the leaf switches. And we can actually use these as models for, let's say, our development environment or development tenant. We could export, change anything we need, essentially copy, and push this over to a test or QA tenant. And then we could add what we need. And then we could essentially export, change whatever we need, and copy this over to our production tenant or production environment. And all of these could be running side by side on the same leaf switches. Now, let's say all of a sudden an application goes away and we don't need it anymore. We could delete a single tenant with, or even just a single application network profile from the fabric, and it's going to go out and it's going to remove all constructs that we're using, or any leaf switches resources that we're using the constructs from this either full tenant or even a sub of the tenant, which is a application network profile, the profile of the application as it pertained to the network. Now, this is one of the other large things that most people in environments don't do. So for instance, what's the largest ACL you've ever seen? The largest I've ever seen is 40,000. I talked to someone the other day that actually had seen a 60,000 ACE, or application control entry line, ACL. Okay, why do they grow that large? Because people are afraid to remove the cruft. They're afraid to go out and remove any of the old configuration, with good reason. In the same way that if you forgot to add the add command to a switch port trunk allowed VLAN, you very well, if you remove some lines of an ACL without a lot of planning, you could very well accidentally take down a lot of production traffic and cost the company hundreds of thousands, possibly, very possibly, millions of dollars, depending on how long it was down. So with ACI, if we know that we're done with an application and we've spent our time planning that, I can simply remove the ANP, the application network profile, and it will go destroy everything else associated with that without impacting any other traffic. It will deprovision my firewalls, deprovision my partitions in my load balancers, or even entire load balancers. It will take care of all of that. So let's talk about the logical model overview. We already began to talk about, if you remember, UCS and stateless computing, taking the idea of our storage specifics, the server specifics for BIOS and firmware and adapters, and our network specifics, and packaging that in a stateless, abstracted construct or framework called a service profile. Well, now we're doing stateless networking. So we have these application network profiles with our endpoint groups and our contracts of defining what an endpoint group exposes to other application tiers, as well as how. Now we have stateless filtering. We actually also now have stateful filtering. So let's define some terms. We've really gone over these, but we'll just have them here on a page for your reference. So an endpoint group, or EPG as we'll refer to it after this. These are containers for objects, or virtual machines, hosts, could be routers, could be switches, that all require the same policy treatment. A tenant. This is a high-level logical separation for a customer or a business unit or a work group or whatever. A tenant is something that we really don't have a equal to in traditional networking. You might think of it loosely like a VDC in an Nexus 7K, although a VDC is actually a separation of physical traffic as well. And a tenant in ACI to some degree that we'll unpack later, has a separation of physical traffic, but we have another way of doing that, which is our layer 3 VRFs or contexts. So a tenant does require a new VRF. There's no way to have two tenants. Well, actually, that's not even true. There really is. We even could have two tenants share a VRF. So a tenant is mainly a logical separation of administrative functions. And again, this is only, I've gone on a lot of, worked with a lot of cloud, public and private cloud deployments and designs. And everyone wants to use separate tenants. It's not always necessary. It just depends on who or what is going to be accessing the ACI APIC directly. If you have multiple groups that are never going to touch through the API programmatic interface or directly through the web GUI, they're never going to touch the actual APIC controller, then you don't need separate tenants. Okay? But you do have that as an option for separating administrative control. We then have our private network, what ACI calls a private network. Now this is a layer 3 context or a VRF. We then have a bridge domain. It is not a VLAN. It's actually a VXLAN segment. Okay? So this can be used to define a layer 2 boundary. We also have subnets within our bridge domains, and we can have multiple subnets within a single bridge domain for the reasons that I talked about earlier. We used to be able to have multiple subnets for a VLAN on an SVI, an IP address, and then secondary. We didn't, but that was because of a lot of broadcast traffic. We can eliminate that broadcast traffic by turning off, and like I said, on our bridge domains in ACI, by default they are off for ARP flooding and unknown unicast flooding. So as long as we leave them off, we can very safely have multiple subnets. And we'll talk about any implications of those as we go on. Contracts, they represent the policies between our endpoint groups. They're provided by one EPG and consumed by another. So the provider is the one that has the services you want to access. So a web tier would provide port 80 and port 443, for instance. And then the users, the outside users, would consume that. Now, one of the things that we'll go over in a lot more detail much later, especially as we begin talking about more details about all of these specific things in ACI, but then also as we begin talking about the RESTful APIs later, is this concept of the management information model. So everything in ACI is a managed object, okay, an MO or managed object. And this management information model or management information tree basically goes as such. We have our top layer, which is our tenant. Technically, we have the top layer, which is the universe, uni, or root. And then under that, we have one or multiple tenants. Within a tenant, that's where we create our application network profile. And notice that one tenant can have many application network profiles. So it's a 1 to n relationship, or a 1 to many. On the contrary, an application network profile, an ANP, can only belong to one tenant. It's an N to 1. One tenant can have multiple layer 2 or layer 3 outside networks. It can have multiple bridge domains. The bridge domain has to be a part of one VRF or private network or context. They're called, all three are the same thing. Okay, so that's an N to 1. But one VRF could have 1 to n could have multiple different bridge domains. A bridge domain can have many subnets, but a subnet can only belong to one bridge domain. Our ANPs can contain many EPGs, but the EPGs can only be a part each individually of one ANP. And of course, the EPGs must actually belong or be mapped to a bridge domain. But of course, one bridge domain can have many EPGs. And this is actually an N-to-N, doesn't show the other N over here, but the EPGs are an N-to-N. So there can, any number of EPGs can have any number of contracts. Contracts, and we'll talk a lot more about these in detail later, contain one or more subjects, and then subjects contain the filters, and subjects to filters are also an N-to-N relationship. Okay, so we can have one subject per contract. actually, sorry, we can have multiple subjects per contract, but a subject, what I meant to say is, can only belong to one contract. But then the actual filters, the ports, the ACEs, if you will, inside of an ACL. Think of a contract like an ACL for stateful or stateless firewalling. There are ACEs or filters, and subjects can have multiple filters. Now, of course, the contracts are not only ACLs, they can also redirect to layer 4 through 7 services. So here's a little bit more complete construct or framework of an ANP, and we'll actually begin adding on to this as we go on. So for instance, we have our database EPG with multiple endpoints that's providing a MySQL SQL contract being consumed by the application EPG. The app EPG has its endpoints, and it's providing a Java contract for Tomcat being consumed by the web EPG, which has its web server endpoints, and it's providing the web-based contract over to the public outside with multiple subnets. All of these belong inside of a layer 3 VRF or context. They could belong in multiple. And then each of these EPGs is mapped to a single bridge domain. They could share bridge domains, so web and app could both be a part of the same bridge domain. And we'll talk later about design aspects of when you might and when you won't use, at least for now, multiple EPGs within a single bridge domain. But in a simple model like this, it would be perfectly fine if all three shared the same VXLAN bridge domain. So this was the logical model. In order for this to be pushed down or instantiated to the fabric, we need to have an understanding of the concrete model. So first of all, how do we apply policy to endpoints? Well, the endpoint attaches to the fabric. The APIC detects the endpoint and learns its source EPG, and we'll talk about how it learns that, how we know what endpoint, VM, router, switch, bare metal machine, how it goes or gets classified into which EPG, and that's designated as its source EPG. And then the APIC pushes the required policy down to the leaf switch. So does that source EPG have a particular bridge domain? Well, it has to. Okay? So what VXLAN VNI is going to be added as a VTEP, or which leaf switch, I guess I should say, is going to be a VTEP and have pushed down for a particular VXLAN VNI, or virtual or VXLAN network identifier. Which VRFs need to be instantiated? Okay, which ACL policies? So the APIC manages pushing of this policy to the leaf and enforcement, and the leaf becomes the enforcement point when the endpoints connect. So you don't have to know all of this right now, but here is a kind of an overview of the APIC controller having a policy controller as a subset of it, a logical model that we've defined, and then the policy update being pushed down. So this is actually to the subset of the logical model. And again, you don't have to understand all this right now. We'll go into a lot more detail later when we talk about the API and programming of ACI, which will probably be one of the last modules once we understand what's happening. This renders implicitly a concrete model, and basically how does that apply to ports, line cards, physical interfaces, VLANs, VRFs, switch nodes. This gets added to the NXOS process, which is running on the leaf switch in the Linux distribution, and deployed to the actual network gear itself.